Step outside on this quiet evening. Let your eyes adjust to the darkness above. The night sky stretches like an endless ocean over your head. Each point of light tells a story that began long before you drew your first breath. Tonight, you are about to discover something wonderful. Something that will change the way you see those distant stars forever. You have always known that Earth holds oceans. You have felt their waves against your feet. You have tasted salt on your lips. You have watched sunlight dance across their surfaces like scattered diamonds. But what if you learned that Earth is not alone in holding these precious waters? Look up at the constellation Orion. See his belt of 3 bright stars? Around one of those stars, a world spins in the darkness. A world where water might flow beneath sheets of ice thicker than mountains. This is not science fiction. This is the universe you live in. Your eyes move from star to star. Behind each pinprick of light, planets dance their slow orbits through space. Some are balls of rock and metal. Others are giants made of swirling gas. But scattered among them are worlds that hold something magical. Something that makes life possible. Water. Not just drops or puddles. Entire oceans. Seas that dwarf the Pacific. Lakes that could swallow continents. These hidden waters exist in places you might never expect. Beneath the frozen surfaces of distant moons. In the temperate zones around red dwarf stars. In the deep spaces between ice and rock. You breathe in the cool night air. Each breath connects you to something larger than yourself. The oxygen in your lungs came from ancient seas on Earth. It was born when the first life forms learned to split water molecules and release this precious gas. The same process might be happening right now on worlds you cannot see. Scientists have names for these distant worlds. They call them exoplanets. The word means planets beyond. Beyond our solar system. Beyond our sun's gentle warmth. Beyond the familiar dance of Mercury, Venus, Mars, and Jupiter. But these distant worlds are not truly beyond reach. Not in your imagination. Not in the light that travels from their stars to your eyes. Every photon that touches your retina has journeyed across the vast emptiness of space. Some of this light has bounced off clouds of water vapor. Some has passed through atmospheres thick with the chemistry of possible life. The nearest star system to Earth is called Alpha Centauri. It sits just over 4 light-years away. If you could travel at the speed of light, you could reach it in 4 years and 3 months. Around one of its stars spins a world called Proxima Centauri b. This planet might hold water on its surface. Liquid water. Flowing water. Water that could cradle the first stirrings of life. For light years sounds impossibly far. But remember this, the light from that star system left its source when you were 4 years younger. The photons touching your eyes right now began their journey in the past. They carry information about worlds that exist in this very moment. You are connected to these distant oceans through the language of light. Think about Earth's oceans for a moment. They cover more than 70% of your planet's surface. They reach depths of 7 miles in some places. They hold enough water to bury every continent under 2 miles of liquid. These oceans took billions of years to form. They witnessed the birth of the first life. They cradled evolution itself. Now multiply that wonder by the number of stars you can see. Multiply it by the stars you cannot see. Multiply it by the countless worlds that orbit in the habitable zones around their suns. The universe suddenly becomes an ocean of oceans. A sea of seas. Some of these distant waters are warm. They lap against shores under alien sunsets. They evaporate into clouds that rain back down on continents you will never walk. They carve rivers through landscapes painted in colors that have no names in any human language. Other waters hide beneath miles of ice. They exist in permanent darkness. They are warmed not by starlight but by the gravitational pull of giant planets. These hidden seas might be deeper and older than any ocean on Earth. They might hold more water than all of Earth's seas combined. The moon Europa orbits Jupiter like a small, icy pearl. Beneath its frozen surface lies an ocean twice as deep as Earth's deepest trench. This ocean has existed for billions of years. It has never seen sunlight. It has never felt the touch of wind. Yet it might teem with life forms that feed on chemical energy instead of solar power. Saturn's moon Enceladus shoots geysers of water into space. These fountains rise hundreds of miles above its south pole. Space probes have flown through these plumes and tasted their chemistry. They found salt. They found organic molecules. They found the building blocks of life itself. Your imagination can travel to these worlds in seconds. You can picture their alien shores. You can envision their hidden depths. You can wonder about the creatures that might swim in their currents or walk along their coastlines. The universe is vast beyond comprehension. But it is also intimate. The same laws of physics that govern Earth's tides also control the movement of alien seas. The same chemistry that sparked life in Earth's ancient oceans might be unfolding on 1,000 different worlds right now. You are made of star stuff, as the poet Carl Sagan once said. Your body contains elements forged in the hearts of dying stars. The water in your cells once drifted through space as ice crystals. The carbon in your DNA once floated in the atmospheres of distant worlds. Tonight, as you prepare for sleep, you carry within yourself the same materials that might be building life on planets you cannot see. You are connected to the universe not just through light and gravity, but through the very atoms that make you who you are. Close your eyes and imagine floating in a warm, alien sea. Feel the gentle current of another world's tide. Taste the salt of a distant ocean on your lips. You are no longer just a person lying in bed on Earth. You are a citizen of the cosmos. A child of the stars. And in the morning, when you wake, those distant oceans will still be there. Still spinning through space. Still holding their secrets. Still waiting for the day when human eyes might finally see their shores. But that journey begins with a single step into wonder. And wonder begins with questions that drift through your mind like gentle waves, carrying you toward the discovery of worlds where water and possibility dance together beneath foreign stars. Imagine you are floating high above Earth. So high that the curve of the planet spreads beneath you like a perfect sphere. From this distance, your home looks impossibly small. A tiny blue marble suspended in the black velvet of space. This is how the Voyager spacecraft saw Earth in 1990. From 4 billion miles away, our entire world appeared as a single pixel of light. A pale blue dot, as Carl Sagan called it. Everything you have ever known, every person who has ever lived, every ocean that has ever lapped against a shore, existed on that one small point of light. But that pale blue dot is extraordinary. It is blue because of water. Vast oceans that cover most of its surface. These waters have been moving and changing for nearly 4 billion years. They have watched mountains rise and fall. They have cradled the first sparks of life. They have shaped the weather, carved the continents, and made your world a living planet. You are looking at the only world where humans know for certain that life exists. Earth's oceans began as a gift from space. Long ago, when your planet was young and hot, comets crashed into its surface like frozen snowballs. Each impact brought water from the far reaches of the solar system. Slowly, over millions of years, these cosmic deliveries filled the low places between the continents. The early Earth was not the peaceful blue world you know today. Volcanoes erupted constantly. The atmosphere was thick with steam and toxic gases. Lightning crackled through skies that had never seen a bird or felt the touch of wind-blown seeds. Yet even then, water was finding its way into every crack and hollow. As the planet cooled, the steam condensed. Rain fell for thousands of years without stopping. Rivers carved their first channels. Lakes filled and overflowed. And finally, the oceans found their boundaries and began the slow work of creating life. Your blue marble holds about 326 million trillion gallons of water. That number is so large it becomes meaningless. Instead, picture this: if all of Earth's water were gathered into a single drop, that drop would be about 860 miles across. It would be larger than most countries. Yet from space, it would still look small compared to the continents. Most of this water is salty. Only 3% is fresh enough for you to drink. Most of that fresh water is locked away in ice caps and glacier. Less than 1% flows in the rivers and lakes that sustain life on land. Yet this tiny fraction of Earth's water has shaped entire civilizations. The blue color that makes Earth so beautiful comes from the way water absorbs light. Water soaks up the red and yellow wavelengths of sunlight. It reflects the blue wavelengths back towards space. This is why the ocean looks blue on a clear day. This is why Earth glows like a sapphire against the darkness. But you are not here just to admire your home planet. You are here to understand that Earth might not be alone in wearing this blue badge of life. Across the galaxy, other worlds orbit other stars. Many of these planets are nothing like Earth. Some are giant balls of gas with no solid surface. Others are rocky worlds locked in eternal ice or scorched by their sun's heat. But scattered among them are worlds that might share Earth's most precious gift: water. These planets exist in what scientists call the habitable zone. Sometimes they call it the Goldilocks zone, after the fairy tale girl who found porridge that was not too hot and not too cold, but just right. This is the distance from a star where water can exist as a liquid. Too close to the star, and water boils away into space. Too far away, and it freezes solid. But in that perfect middle distance, water can pool and flow. It can dissolve minerals. It can carry nutrients. It can become the stage where chemistry transforms into biology. Around a star called Kepler for 52, there spins a planet that might be Earth's cousin. This world is slightly larger than your home. It orbits in the habitable zone of a sun-like star. It has existed for 6 billion years, long enough for complex life to evolve if the conditions were right. Nobody knows what this distant world looks like. It might be covered in deep oceans. It might have continents and islands. It might have clouds and storms and seasons. Or it might be a desert world where water exists only in underground rivers. But the possibility exists that somewhere in the constellation Cygnus, waves are lapping against an alien shore. The star TRAPPIST-1 holds 7 planets in its gravitational embrace. 3 of these worlds sit in the habitable zone. They are close enough to each other that if you stood on one, the others would appear larger in the sky than Earth's moon. These planets might share their water through the thin atmosphere of space. Meteors knocked loose from one world might carry water and even microbes to its neighbors. You can think of these distant worlds as Earth's cosmic siblings. They formed from the same basic materials. They follow the same laws of physics. They respond to the same forces that shaped your home planet. If Earth could support life, then perhaps they could too. Some of these worlds might be better at supporting life than Earth itself. They might have more stable climates. They might have stronger magnetic fields to protect their atmospheres from harmful radiation. They might have larger oceans or more favorable chemical conditions. Scientists have found over 5,000 planets orbiting other stars. Many of these worlds exist in the habitable zones of their suns. Some are rocky like Earth. Others might be water worlds with oceans hundreds of miles deep. A few might have surfaces covered entirely by liquid water, with no continents breaking the endless expanse of alien seas. The universe suddenly becomes a much more interesting place when you realize that Earth's blue marble might have thousands of distant cousins. Each one spinning through space. Each one possibly holding its own version of the miracle you call home. Your pale blue dot is not just beautiful. It is a proof of concept. It is evidence that rocky planets can hold liquid water. It demonstrates that water worlds can develop complex chemistry. It shows that given enough time, chemistry can become biology. And if it happened here, in this ordinary corner of an ordinary galaxy, then it might be happening everywhere. Tonight, as you rest beneath the blanket of Earth's protective atmosphere, remember that you live on a water world. A rare and precious oasis in the cosmic desert. But perhaps not as rare as people once believed. Perhaps, scattered across the galaxy like drops of rain on a vast plain, Other blue marbles are catching starlight and reflecting it back into space, each one a small beacon of possibility in the endless night. 400 years ago, a man named Johannes Kepler stared at the night sky and dreamed of understanding the dance of planets. He lived in a world without electric lights. The stars blazed overhead with a brightness you can barely imagine. Night after night, he watched Mars trace its path across the darkness. He calculated and measured and wondered. Kepler discovered that planets move in oval-shaped paths around their stars. These orbits follow patterns as precise as clockwork, as predictable as the beating of a heart. His mathematical laws still guide spacecraft today. They help scientists understand how worlds move through space. In 2009, NASA launched a space telescope and named it after this ancient dreamer. The Kepler Space Telescope became humanity's greatest planet hunter. It carried a simple but brilliant idea into the darkness between stars. You can understand this idea by watching a moth fly in front of a porch light. For just a moment, the moth blocks some of the light. The bulb dims slightly. If you were watching carefully, you would notice this tiny change in brightness. You would know something had passed between you and the light. Kepler uses this same principle to find planets around distant stars. It watches thousands of stars at once. It measures their brightness with incredible precision. When a planet passes in front of its star, the star dims just a little bit. Kepler notices this dimming and whispers to us across the void, "Here is another world." The dimming lasts only a few hours. Sometimes less. It is so small that Kepler must be thousands of times more sensitive than your eyes. If a star's brightness is like a bonfire, the planet's shadow is like holding a grain of sand in front of the flames. Yet Kepler can detect even this tiny interruption of starlight. This method is called the transit technique. Transit means to pass across. Each time a planet transits its star, it creates a signature of dimmed light. This signature tells scientists many things about the distant world. The depth of the dimming reveals the planet's size. A large planet blocks more light than a small one. Jupiter would create a deep dimming. Earth would create a shallow one. Mars would create an even more delicate shadow. The time between transits tells scientists how long the planet takes to orbit its star. A planet close to its star completes its orbit quickly. A planet far away takes much longer. Earth completes its orbit in 365 days. Some planets Kepler has found orbit their stars in just a few hours. Others take hundreds of Earth years to complete one trip around their sun. The shape of the dimming curve reveals details about the planet's atmosphere. If the planet has thick clouds or rings, the light changes in special ways. Sometimes the star's light filters through the edge of the planet's atmosphere. This filtered light carries the chemical fingerprints of gases that might include water vapor. Imagine you are floating in space beside the Kepler telescope. You are both drifting in the darkness beyond Earth's atmosphere. Below you, Earth slowly turns in its orbit around the Sun. Ahead of you, Kepler's great eye stares unblinking at a patch of sky in the constellation Cygnus. In that single patch of sky, no larger than your hand held at arm's length, Kepler watches 150,000 stars. Every 30 minutes, it takes a photograph of this entire region. It measures the brightness of each star. It stores this information and sends it back to Earth. Scientists on Earth receive this data and search for the telltale dimming that signals a planet. They look for patterns that repeat. They check for other explanations. Sometimes what looks like a planet is actually two stars orbiting each other. Sometimes it is a sunspot moving across a star's surface. But sometimes, wonderfully, it is exactly what it appears to be, a distant world crossing the face of its sun. Over 9 years, Kepler discovered more than 2,600 confirmed planets. It found evidence of thousands more worlds waiting for further study. It revolutionized our understanding of how common planets are in the galaxy. Before Kepler, scientists could only guess about planetary systems around other stars. They wondered if our solar system was rare or common. They debated whether most stars had planets at all. Kepler provided the answer with overwhelming clarity: planets are everywhere. Some of Kepler's discoveries challenged everything scientists thought they knew about planetary systems. It found planets larger than Jupiter orbiting closer to their stars than Mercury orbits the Sun. These hot Jupiters complete their orbits in a matter of days. Their surfaces are heated to thousands of degrees. It found planets made entirely of rock that are larger than Neptune. These super-Earths have no equivalent in our solar system. They might have thick atmospheres or vast oceans. They might be the most common type of planet in the galaxy. It found systems where multiple planets orbit so close to each other that their gravity creates complex rhythms. These planets are locked in gravitational resonance, like dancers moving to the same cosmic music. When one planet completes 2 orbits, another completes exactly 3. When one finishes 4 orbits, another finishes exactly 6. Most importantly for your journey tonight, Kepler found planets in the habitable zones of their stars. Worlds where liquid water might exist. Candidates for supporting life as we know it. Kepler for 52b orbits a Sun-like star in the constellation Cygnus. This planet is only 60% larger than Earth. It receives almost the same amount of energy from its star as Earth receives from the Sun. It might have liquid water on its surface. It might have clouds and weather and seasons. Kepler's 186f was the first Earth-sized planet found in the habitable zone of another star. It orbits a red dwarf star smaller and cooler than our Sun. Days on this world would be different from Earth days. The star would appear larger in the sky but dimmer. Plants might evolve to capture the red light instead of the yellow light Earth's plants use. The TRAPPIST-1 system, first detected by ground-based telescopes and confirmed by other instruments, shows what Kepler's legacy made possible. 7 planets orbit a tiny red star just 40 light-years away. 3 of these worlds sit in the habitable zone. They are so close to each other that standing on one, you could see the others as disks in the sky, larger than Earth's moon appears to you. Each discovery builds on the work that came before. Each new technique reveals details that earlier methods missed. The transit method that Kepler perfected has become the foundation for an entire generation of planet-hunting missions. Tonight, as you drift toward sleep, Kepler's data continues to flow to Earth. New planets hide in measurements already taken. Scientists are still analyzing light curves from observations made years ago. Each flash of dim starlight might hold the key to finding humanity's next cosmic neighbor. The ancient dreamer Johannes Kepler could never have imagined that his mathematical laws would guide a telescope to discover thousands of distant worlds. But perhaps he would have smiled to know that humanity never stopped looking up at the stars and wondering what secrets lay hidden in their light. And in that light, carried across the vast distances of space, lie stories of worlds where the gentle balance of temperature and chemistry might have created something even more precious than we ever dared to hope. Once upon a time, a curious girl named Goldilocks wandered into a house in the forest. She found 3 bowls of porridge on the table. The first was too hot and burned her tongue. The second was too cold and had no warmth at all. But the third bowl was just right. Not too hot, not too cold, but perfectly comfortable for her to enjoy. This simple fairy tale has given scientists a beautiful way to describe one of the most important concepts in the search for life beyond Earth. Around every star in the universe, there exists a special zone. A place that is not too hot and not too cold. A region where water can exist as a liquid. Scientists call this the habitable zone, but many people know it by its nickname, the Goldilocks zone. Imagine you are standing next to a campfire on a cool evening. If you stand too close, the heat becomes uncomfortable. Your face burns and you must step away. If you stand too far back, the fire's warmth cannot reach you. You feel cold and want to move closer. But somewhere in between, there is a perfect distance. Close enough to feel the fire's gentle warmth. Far enough away to avoid being burned. Stars work the same way. They pour energy into space like cosmic campfires. Planets that orbit too close become furnaces where water boils away into steam. Planets that orbit too far become frozen worlds where water turns to ice and never melts. But in that perfect middle distance, water can exist in all 3 forms: ice, liquid, and vapor. This is where the magic of life becomes possible. Water is not just any chemical compound. It is the foundation of all life as we know it. Your body is more than 60% water. Every cell in your body floats in a tiny ocean of liquid water. Your blood is mostly water, carrying nutrients and oxygen to every corner of your being. Your brain, your muscles, your bones, all depend on water to function. Water has special properties that make it perfect for supporting life. It can dissolve more substances than almost any other liquid. This means it can carry nutrients, minerals, and waste products wherever they need to go. It can flow through the tiniest spaces between cells. It can form drops that cling together or spread out in thin films. Water also holds heat very well. This helps stabilize temperatures on planets that have large oceans. During the day, the oceans absorb heat from the star. At night, they slowly release this heat back into the atmosphere. This creates a gentle, stable climate instead of extreme swings between hot and cold. When water changes from liquid to gas, it absorbs energy. When it changes from gas back to liquid, it releases energy. This constant cycling of evaporation and condensation helps move heat around a planet's surface. It creates weather patterns, drives ocean currents, and makes climates more moderate. The habitable zone around each star is different. It depends on how hot the star burns and how much energy it pours into space. Our Sun is a medium-sized star with a moderate temperature. Earth sits comfortably in the middle of our Sun's habitable zone. Venus orbits too close and has become a hellish greenhouse where surface temperatures reach 900 degrees Fahrenheit. Mars orbits near the outer edge and has become a cold desert where liquid water cannot survive on the surface. But our Sun is just one star among hundreds of billions. Each star has its own habitable zone. Some stars are much larger and hotter than our Sun. These giant stars create habitable zones that stretch much farther out into space. A planet would need to orbit at the distance of Jupiter or Saturn to find the right temperature for liquid water. Other stars are much smaller and cooler than our Sun. Red dwarf stars are the most common type of star in the galaxy. They burn their fuel slowly and can shine for trillions of years. Their habitable zones are much closer in. A planet would need to orbit as close as Mercury does to our Sun to receive enough warmth for liquid water. This creates interesting possibilities. Planets in the habitable zones of red dwarf stars would have very long days and nights. They might become tidally locked, with one side always facing the star and the other side always facing away. The day side could have temperatures warm enough for liquid water. The night side could be frozen solid. But in the zone between day and night, in the eternal twilight, conditions might be just right for life. Some planets might have thick atmospheres that help distribute heat around their surfaces. Others might have large moons that create tides and help mix their oceans. Some might have active volcanoes that add heat from within. All of these factors can help expand the effective habitable zone around a star. Scientists have discovered thousands of planets that orbit within the habitable zones of their stars. Some are larger than Earth and might be covered by deep oceans with no dry land at all. These water worlds could have seas hundreds of miles deep. Life on such planets might exist entirely in the ocean, never knowing the touch of air or sunlight. Others are smaller and rockier, more like Earth. They might have continents and islands, lakes and rivers, ice caps and tropical seas. They might have weather patterns driven by the evaporation and condensation of water. They might have seasons caused by the tilt of their rotation axis. The planet Kepler for 42b orbits in the habitable zone of an orange dwarf star 1,200 light-years away. It is about 1/3 larger than Earth and receives about 2/3 as much energy from its star as Earth receives from the Sun. If it has the right atmosphere, liquid water could flow on its surface. Kepler 62f sits near the outer edge of its star's habitable zone. It might be covered entirely by water, like a cosmic ocean with no land. The planet is 40% larger than Earth and orbits a star that is smaller and cooler than our Sun. Its year lasts 267 Earth days. TOI 715b was discovered recently, orbiting in the habitable zone of a red dwarf star just 137 light-years away. This planet is about 1.5 times the size of Earth. It orbits so close to its small, dim star that its year lasts only 19 Earth days. Each of these worlds represents a different solution to the same fundamental challenge: how to maintain liquid water on a planetary surface. The answers vary widely. Some planets might have thick, cloudy atmospheres that trap heat like a blanket. Others might have thin atmospheres and depend on greenhouse gases to stay warm. Some might have large moons that create tidal heating. Others might orbit binary stars that provide warmth from two different sources. The habitable zone is not a fixed boundary. It changes as stars age and evolve. Our Sun was dimmer in the past, which means Earth was closer to the outer edge of the habitable zone billions of years ago. As our Sun ages and grows brighter, the habitable zone will slowly move outward. In about 1 billion years, Earth will become too hot for liquid water, while Mars might warm up enough to support flowing rivers again. This cosmic dance of heating and cooling, of water freezing and thawing, has been happening throughout the history of the universe. For billions of years, countless worlds have found themselves in the perfect position to support liquid water. Some have kept this precious gift. Others have lost it as their stars evolved or their orbits changed. Tonight, as you rest in the perfect temperature of your own Goldilocks zone, your warm bed in your comfortable room, you can imagine countless other worlds finding their own perfect balance. Somewhere in the galaxy, water is pooling in an alien valley for the first time. Somewhere else, it is flowing down mountainsides toward a waiting sea. And in that flowing water, in that perfect balance of temperature and chemistry, the first stirring of something more complex than simple molecules might be beginning to wake. Close your eyes and imagine floating in the cold darkness of space, far beyond Mars, in the realm of Jupiter. Before you spins a moon that looks like a giant marble made of ice. Its surface gleams pale and smooth, crossed by dark lines that curve and intersect like cracks in a frozen pond. This is Europa, one of Jupiter's largest moons, and it holds one of the most beautiful secrets in the solar system. Europa is slightly smaller than Earth's moon, but it could not be more different. While our moon is dry and dusty, Europa is a world of hidden water. Beneath its frozen shell lies an ocean that has never seen sunlight. An ocean that may contain twice as much water as all of Earth's seas combined. You cannot see this ocean from space. Europa's surface is a shell of ice 15 to 20 miles thick. But scientists have discovered its liquid secret through careful observation and detective work that reads the story written in the moon's behavior. Jupiter is enormous. Its mass is more than twice that of all the other planets combined. This giant planet pulls on Europa with tremendous force, but Europa is not alone in feeling Jupiter's gravity. 3 other large moons orbit nearby: Io, Ganymede, and Callisto. These moons tug on Europa too, creating a gravitational dance that has continued for billions of years. As Europa orbits Jupiter, these gravitational forces stretch and squeeze the moon like a rubber ball. When Europa is closest to Jupiter, the gravity pulls strongest. When it swings farther away, the force weakens. This constant flexing generates heat inside Europa, the same way a wire heats up when you bend it back and forth repeatedly. This tidal heating is what keeps Europa's ocean liquid. Without it, the moon would be frozen solid, just another ice ball drifting through space. But the endless gravitational massage from Jupiter warms Europa from within, maintaining an ocean that has existed for perhaps 4 billion years. The surface of Europa tells this story in a language of ice and motion. Long ridges stretch across the landscape like scars. Some of these ridges run for thousands of miles, longer than the distance from New York to Los Angeles. They form when the tidal forces crack the ice shell and then heal the cracks with fresh ice from below. Between the ridges lie areas called chaos terrain, where the surface has broken apart and reformed in complex patterns. Imagine a jigsaw puzzle where the pieces have been moved around and new pieces added. This is what happens when Europa's ocean pushes up against the ice shell, breaking it apart and creating new surface features. The dark lines that cross Europa's surface may be places where the ocean has reached almost to the surface. These features suggest that the ice shell is dynamic and active, constantly changing as the hidden sea moves beneath it. Some scientists think these dark lines might be places where organic chemicals from the ocean have stained the ice. You can picture Europa's ocean as an alien sea darker than any place on Earth. No sunlight has ever penetrated to its depths. The water is kept liquid not by warmth from above but by heat generated from within. The ocean floor, miles below the ice, might be dotted with underwater volcanoes called hydrothermal vents. These vents would create oases of warmth in the cold depths. Around each vent, minerals from Europa's rocky core would dissolve into the water, creating the chemical ingredients that life needs to survive. On Earth, hydrothermal vents in our deepest ocean support entire ecosystems of creatures that never see the sun. They feed on chemicals instead of sunlight, creating a completely different kind of food chain. Europa's ocean might harbor similar communities. Microscopic life forms could cluster around the warm vents, feeding on sulfur compounds and other chemicals. Larger creatures might evolve to eat the smaller ones. Over billions of years, evolution could craft entire ecosystems in the eternal darkness beneath the ice. The water in Europa's ocean is probably salty, like Earth's seas. This salt comes from reactions between the ocean and Europa's rocky interior. Salt water conducts electricity better than pure water, and this might explain some of the magnetic field changes that spacecraft have detected around Europa. When the Voyager spacecraft first photographed Europa in 1979, scientists were amazed by its smooth, bright surface. Later, the Galileo mission spent years studying the Moon in detail, mapping its features and measuring its magnetic properties. These observations revealed the likely existence of the subsurface ocean and made Europa one of the most exciting targets in the search for extraterrestrial life. The ice shell that covers Europa's ocean might be thinner in some places than others. Scientists have found evidence of water plumes shooting up from the surface, similar to the geysers on Saturn's moon Enceladus. These plumes could carry samples of the ocean water into space, where future missions might collect them and analyze their chemistry. Imagine standing on Europa's surface in a protective spacesuit. The ice beneath your feet would feel solid, but you would know that far below, dark waters flow in currents you cannot see. The silence would be complete. Europa has no atmosphere to carry sound. Above you, Jupiter would dominate the sky, appearing 11 times larger than the full moon looks from Earth. The giant planet would show phases like Earth's moon, cycling from full to crescent as Europa orbits. Jupiter's colorful cloud bands would shift and swirl, creating a constantly changing masterpiece in the black sky. Sometimes you might see Io, Europa's volcanic neighbor, passing like a yellow dot across Jupiter's face. Europa's day and night cycle lasts about 3.5 Earth days. But the temperature hardly changes between day and night. The surface stays at a frigid -260 degrees Fahrenheit, cold enough to freeze the air you breathe instantly. Only the hidden ocean remains warm enough for liquid water to exist. Future missions to Europa are already being planned. The Europa Clipper spacecraft will orbit Jupiter and make dozens of close flybys of the icy moon. It will use radar to peer through the ice shell and map the ocean beneath. It will analyze any water plumes it encounters. It will study Europa's chemistry and search for the building blocks of life. Some scientists dream of sending a submarine to Europa's ocean. This robotic explorer would first have to melt through miles of ice, then deploy into the alien sea. It would carry lights to illuminate the eternal darkness. It would search for signs of life in the most remote ocean in the solar system. The possibility that life exists in Europa's hidden sea captures the imagination because it expands the places where life might survive. If organisms can thrive in Europa's dark ocean, then similar seas on other moons might also harbor life. The conditions for biology might be more common than we ever imagined. Europa teaches us that an ocean world does not need to orbit in the traditional habitable zone around a star. It can exist anywhere that tidal forces or other heating mechanisms can keep water liquid. This revelation multiplies the number of potentially habitable worlds in the galaxy. Tonight, as you rest in your own warm bed, Europa continues its dance around Jupiter. The tidal forces continue to flex and heat the moon's interior. the dark ocean continues to flow beneath its icy shell. And somewhere in those hidden depths, in the warm oases around underwater vents, chemistry might be taking the first tentative steps toward something more complex. But Europa is not the only moon that guards such secrets. In the realm of Saturn, another small world geysers its hidden ocean directly into space, offering an even more accessible window into the possibilities of life beyond Earth. In the golden realm of Saturn, where rings of ice and dust circle like halos around a giant planet, there exists a small moon that has captured the hearts of scientists and dreamers alike. Enceladus is only 310 miles across, so small that you could drive around its equator in less than a day. Yet this tiny world holds secrets that rival those of much larger planets. From a distance, Enceladus looks like a perfect pearl. Its surface gleams brilliant white, reflecting nearly all the sunlight that touches it. This moon is one of the most reflective objects in the solar system. It shines like fresh snow on a winter morning, unmarked by the dark dust that stains other moons and asteroids. But Enceladus is far from quiet. At its southern pole, something extraordinary happens that sets this little moon apart from all others. Great geysers of water and ice shoot into space, creating fountains that rise hundreds of miles above the surface. These plumes sparkle in Saturn's distant sunlight like cosmic fireworks frozen in slow motion. You can picture these geysers erupting from long cracks in the ice called tiger stripes. Main fractures slice across the South Polar region, each one darker and warmer than the surrounding terrain. These stripes have beautiful names: Alexandria, Baghdad, Cairo, and Damascus. They mark places where Enceladus reveals its hidden ocean to the vacuum of space. The discovery of these water plumes changed everything scientists thought they knew about small moons. For decades, astronomers assumed that worlds as tiny as Enceladus would be frozen solid, with no geological activity at all. The moon seemed too small to retain the internal heat needed to keep water liquid. Yet there it was, shooting ocean water into space like a cosmic whale spouting at the surface of the sea. The Cassini spacecraft, which orbited Saturn for 13 years, made this discovery possible. In 2005, Cassini's cameras first captured images of the mysterious plumes. The spacecraft flew closer and closer to Enceladus, eventually passing just 15 miles above its surface. During these daring flybys, Cassini flew directly through the water geysers, tasting their chemistry with its scientific instruments. What Cassini found amazed everyone. The plumes contained not just water ice, but salt and organic molecules. The salt suggested that liquid water was in contact with rock somewhere beneath the surface, dissolving minerals the way Earth's oceans dissolve salt from the seafloor. The organic molecules hinted at the complex chemistry that might support life. Imagine riding alongside Cassini as it approaches Enceladus for one of these historic flybys. Saturn hangs in the distance like a pale yellow giant, its rings edge-on and nearly invisible. Enceladus grows larger in your view, transforming from a point of light into a world of ice and mystery. The southern hemisphere comes into view, and suddenly you see them, towering columns of water vapor and ice crystals shooting into space. The spacecraft's instruments go to work immediately. The mass spectrometer tastes the chemical composition of the plumes. The cosmic dust analyzer counts particles of ice and measures their size. The magnetometer detects changes in Saturn's magnetic field caused by electrically charged particles in the water vapor. Camera shutters click rapidly, capturing images that will be studied for years. As Cassini flies through the densest part of the plume, ice crystals pepper the spacecraft like hail. Each particle tells a story about the hidden ocean far below. Some crystals contain more salt than others, suggesting that the underground sea has currents and mixing patterns. Some carry organic molecules that formed in the dark depths where water meets rock. The tiger stripes themselves are warmer than the rest of Enceladus. While most of the moon's surface stays at -330 degrees Fahrenheit, the fractures reach temperatures as warm as -135 degrees. This might sound impossibly cold to you, but in the context of the outer solar system, these temperatures are practically balmy. Heat flows up from inside Enceladus through these fractures. The source of this heat puzzled scientists for years. The moon seemed too small to generate significant tidal heating like Europa does around Jupiter. Eventually, researchers realized that Enceladus does experience tidal forces from Saturn, but in a more subtle way. The moon's orbit is slightly oval-shaped, causing it to speed up and slow down as it circles the giant planet. This creates just enough flexing to keep parts of the interior warm. The underground ocean of Enceladus lies beneath about 20 miles of ice at the South Pole. This sea might be 6 miles deep, making it relatively shallow compared to Europa's ocean. But what it lacks in depth, it makes up for in accessibility. While Europa keeps its ocean locked away beneath a thick shell, Enceladus generously shares samples of its sea with anyone who cares to collect them. Scientists have calculated that the geysers shoot about 440 pounds of water into space every second. Most of this water falls back to the surface as snow, creating a constantly renewed landscape of fresh ice. But some escapes Enceladus entirely and forms a thin ring of water vapor around Saturn. You are connected to this distant moon through the particles it has scattered throughout the Saturnian system. The chemistry of Enceladus's plumes tells a story of hydrothermal activity on the ocean floor. The water contains silica particles that could only form at temperatures of at least 200 degrees Fahrenheit. This suggests that hot springs or hydrothermal vents warm the seafloor, creating environments that could support life even in the eternal darkness beneath the ice. On Earth, hydrothermal vents teem with unique forms of life. Bacteria feed on chemical energy instead of sunlight. Tubeworms, crabs, and fish create ecosystems that thrive in complete darkness. The discovery of similar conditions on Enceladus raises the exciting possibility that life might exist there too, sustained by the same chemical processes that support deep-sea life on our own planet. The organic molecules detected in Enceladus's plumes include some of the building blocks of life. Scientists have found methane, formaldehyde, and other carbon-based compounds that form when hot water reacts with rock. These are not signs of life itself, but they show that the chemistry needed for biology is present in the moon's hidden ocean. Future missions to Enceladus could sample these plumes in even greater detail. A spacecraft could collect water droplets and ice crystals, then analyze them with instruments far more sophisticated than Cassini carried. Such a mission might detect amino acids, proteins, or even microscopic organisms if they exist in the subsurface sea. The beauty of Enceladus lies not just in its gleaming surface and spectacular geysers, but in what it represents for the search for life beyond Earth. This small moon shows that habitable environments might exist in the most unexpected places. You do not need a large planet in the perfect orbit around a sun-like star. Sometimes all you need is a small world with the right internal chemistry and enough tidal heating to keep water liquid. Enceladus has expanded our definition of where life might thrive. Its success in maintaining an active ocean has encouraged scientists to look more carefully at other small moons throughout the solar system. Perhaps similar oceans hide beneath the ice of other worlds, waiting to be discovered by future explorers. Tonight, as you drift toward sleep, Enceladus continues its faithful orbit around Saturn. Its geysers continue to paint the space around the ring planet with droplets of alien seawater. Each eruption carries the potential for discovery, the possibility that we are not alone in finding ways to nurture the chemistry of life. And beyond Saturn's realm, in star systems we have only begun to explore, other small worlds might be performing their own quiet miracles, maintaining pockets of warmth and water in the cold vastness between the stars. In the constellation Aquarius, 40 light-years from your bedroom window, there exists a star system that reads like a cosmic fairy tale. 7 planets dance around a small red star in perfect harmony, their orbits timed like the movements of a celestial clockwork. This system, known as TRAPPIST-1, has captured the imagination of scientists and dreamers because it offers not 1, but 7 chances for life to find a home. The star at the center of this system is much smaller and dimmer than our Sun. TRAPPIST-1 is what astronomers call a red dwarf, a type of star that burns its fuel so slowly it could shine for trillions of years. If our Sun is like a bright campfire, TRAPPIST-1 is more like the gentle glow of embers. It produces only 1/1000th the light that our Sun creates. Because their star is so dim, the 7 planets must orbit much closer to receive enough warmth for liquid water. The outermost planet in the TRAPPIST-1 system orbits closer to its star than Mercury orbits our Sun. All 7 worlds could fit comfortably inside the orbit of Venus. They huddle together in the faint warmth of their small red sun like a family gathered around a dying fire. This closeness creates something magical. The planets are so near to each other that if you stood on the surface of one, the others would appear as large disks in the sky. Some would look bigger than our full moon. You could watch them go through phases as they orbit their star, waxing and waning like celestial companions sharing the same small patch of space. The 7 worlds are locked in what scientists call orbital resonance. This means their orbital periods are related by simple whole numbers, like a mathematical song played out across the heavens. For every 8 orbits the innermost planet completes, the next planet completes exactly 5 orbits. The third planet completes 3 orbits for every 2 of the fourth planet. This pattern continues throughout the system, creating a gravitational harmony that has kept the planet stable for billions of years. You can imagine this resonance as a cosmic symphony where each planet plays its own note at precisely the right time. The gravitational tugs between the worlds create a rhythm that prevents any planet from drifting too close to the others or wandering away from the system entirely. This celestial music has been playing since before Earth formed, and it will continue long after our own Sun dies. 3 of the 7 planets orbit in the habitable zone where liquid water could exist on their surfaces. These worlds, designated TRAPPIST-1e, F, and G, receive amounts of energy similar to what Venus, Earth, and Mars receive from our Sun. They represent humanity's best nearby examples of planets that might harbor liquid oceans under alien skies. TRAPPIST-1e sits near the inner edge of the habitable zone. It receives about as much energy from its star as Earth receives from the Sun. If this planet has an atmosphere similar to Earth's, its surface temperature could be perfect for liquid water. Oceans might cover its continents. Clouds might drift through its skies. Rain might fall on shores that have never known the footprint of any earthly creature. TRAPPIST-1f orbits in the middle of the habitable zone, receiving about as much starlight as Mars receives from our Sun. But unlike Mars, TRAPPIST-1f is large enough to hold onto a thick atmosphere. This world might be slightly cooler than Earth, but greenhouse gases in its atmosphere could trap enough heat to keep its surface warm. It might be a world of ice caps and temperate seas, of snowy mountains and flowing rivers. TRAPPIST-1g sits near the outer edge of the habitable zone. It receives less energy than Mars gets from our Sun, but it might still harbor liquid water if it has a very thick atmosphere. This world could be covered entirely by a global ocean beneath a shell of ice, similar to Europa or Enceladus. Or it might have a few areas where geothermal heat keeps the surface warm enough for liquid water to pool in protected valleys. All 7 planets are likely tidally locked to their star, meaning the same side always faces the red dwarf Sun. One hemisphere experiences eternal day while the other knows only endless night. The day side could be scorching hot while the night side remains frozen. But in the twilight zone between eternal day and night, temperatures might be just right for liquid water to exist. This creates fascinating possibilities for climate and weather. Winds would blow constantly from the hot day side toward the cold night side, creating planet-wide weather patterns unlike anything on Earth. The twilight regions might have permanent storms or cloud formations as warm air meets cold air in an endless atmospheric battle. Scientists have begun studying the atmospheres of these distant worlds using space telescopes. When a planet passes in front of its star, some starlight filters through the planet's atmosphere before reaching Earth. This filtered light carries the chemical fingerprints of gases that might exist in alien skies. Early observations suggest that some of the TRAPPIST-1 planets might have substantial atmospheres, while others might be airless worlds with thin or non-existent atmospheres. The discovery of the TRAPPIST-1 system began with a small telescope in Chile called TRAPPIST, which stands for Transiting Planets and Planetesimal Small Telescope. This modest instrument detected the first hints that planets were orbiting the red dwarf star. Follow-up observations with larger telescopes and space-based instruments revealed the full extent of this remarkable system. The proximity of the TRAPPIST-1 system makes it an ideal target for future study. 40 light-years sounds impossibly far, but in astronomical terms it is practically next door. Advanced telescopes now being built will be able to study these planets in unprecedented detail. They might detect water vapor in their atmospheres. They might find oxygen or methane that could indicate the presence of life. Some scientists have suggested that the TRAPPIST-1 planets might share material through impacts from asteroids and comets. A large impact on one world could launch rocks and ice into space. These materials might eventually reach the other planets, potentially spreading life from one world to another if it exists. The system could be a network of interconnected worlds, each influencing the others through the exchange of matter across space. The red dwarf star TRAPPIST-1 is also much more stable than our Sun. Red dwarf stars can shine for trillions of years, far longer than the 10 billion-year lifespan of Sun-like stars. This means the TRAPPIST-1 planets have had enormous amounts of time for life to evolve, and they will continue to have stable conditions for eons into the future. Living on a planet around a red dwarf star would create a very different experience from life on Earth. The star would appear larger but dimmer in the sky, glowing like a giant red coal. Plants might evolve to capture the red light instead of the yellow light that Earth's plants use. The sky might have a permanently reddish tint, creating alien sunsets unlike anything in our earthly experience. The 7 worlds of TRAPPIST-1 remind us that planetary systems can be very different from our own while still offering the possibility of life. This system shows that small, dim stars can nurture families of planets in their gentle warmth. It demonstrates that multiple worlds in a single system might simultaneously support the conditions necessary for biology. Tonight, as you close your eyes, the TRAPPIST-1 system continues its ancient dance. 7 worlds spin in their precise orbits, maintaining the gravitational harmony that has kept them stable for billions of years. 3 of these worlds might have oceans lapping against shores beneath a dim red sun, while alien weather patterns carry water vapor through skies that have never known the touch of earthly rain. And just for light years closer to Earth, around the nearest star to our own Sun, another world waits in the perfect distance from its red dwarf parent, possibly harboring its own version of the miracle we call home. Tonight, as you settle into your bed, turn your thoughts toward the southern constellation Centaurus. There, invisible to your naked eye but closer than any other star, burns a small red ember called Proxima Centauri. This star is humanity's nearest stellar neighbor beyond our own Sun, and it holds a secret that makes it one of the most important discoveries in the history of astronomy. Proxima Centauri is tiny compared to our Sun. If our Sun were a basketball, Proxima would be a tennis ball sitting for miles away. This red dwarf star burns so dimly that even though it is our closest neighbor, you cannot see it without a telescope. It produces only 1/6% of the light that our Sun creates, glowing like a distant candle flame in the cosmic darkness. Yet despite its small size and faint glow, Proxima Centauri cradles a world that might be the most significant planet ever discovered. Proxima Centauri b orbits its small red star every 11 Earth days, circling so close that it receives nearly the same amount of energy that Earth receives from our much brighter Sun. This planet sits squarely in the habitable zone where liquid water could exist on its surface. The distance between you and Proxima Centauri b is almost impossible to imagine. Light from that world takes 4 years and 3 months to reach your eyes. If you could somehow travel at the speed of our fastest spacecraft, the journey would take about 75,000 years. Yet in the vastness of the galaxy, this planet is practically next door, closer to Earth than any other known world beyond our solar system. Proxima Centauri b is likely tidally locked to its star, meaning the same hemisphere always faces the red dwarf Sun. One side of the planet experiences eternal day, baked by the constant heat of its nearby star. The other side knows only endless night, forever turned away from any source of warmth or light. This creates a world divided between extreme heat and bitter cold. But between these two extremes lies a ring of perpetual twilight. In this zone, the star hangs forever low on the horizon like a sunset that never ends. Here, temperatures might be just right for liquid water to exist. Here, in the eternal dawn of an alien world, the chemistry of life might find its perfect balance. Imagine standing on the surface of Proxima Centauri b in this twilight zone. The landscape around you would be bathed in the deep red glow of the star hanging motionless in the sky. The light would be dimmer than Earth's twilight, but steady and constant. No sunrise would ever come to brighten the day. No sunset would ever bring darkness. The star would simply glow in the same position for all eternity. Plants on such a world, if they existed, might evolve to capture the red light of their star instead of the yellow light that Earth's plants use. The landscape might be painted in colors that have no names in any human language. Leaves might be black or deep purple to absorb as much of the dim red light as possible. Flowers might bloom in shades of infrared that your eyes could never see. The temperature differences between the day and night sides would create powerful winds. Hot air from the day side would rush toward the cold night side, while cooler air would flow back to replace it. These winds might be strong enough to carry water vapor around the entire planet, distributing moisture from the day side to the night side and creating weather patterns unlike anything on Earth. On the night side of Proxima Centauri b, the surface might be covered with ice many miles thick. But this ice could hide liquid water beneath, kept warm by the planet's internal heat or by the pressure of the ice itself. Underground rivers might flow through caverns carved in rock, carrying warmth from the planet's core toward the surface. Scientists discovered Proxima Centauri b using a technique called the radial velocity method. They watched the star carefully and noticed that it wobbles slightly as the planet orbits around it. This wobble is incredibly small, causing the star to move back and forth at the speed of a gentle walk. But sensitive instruments can detect this motion by measuring tiny changes in the star's light. The planet is at least 1.3 times more massive than Earth, making it what scientists call a super-Earth. This extra mass means stronger gravity on its surface. If you could somehow visit Proxima Centauri b, you would weigh about 30% more than you do on Earth. Your muscles would have to work harder with every step, but the stronger gravity would also help the planet hold onto its atmosphere more effectively. Whether Proxima Centauri b has an atmosphere remains one of the biggest questions about this world. Red dwarf stars like Proxima Centauri are known for producing powerful flares that blast their planets with radiation. These stellar storms could strip away a planet's atmosphere over millions of years, leaving behind a barren, airless rock. But if Proxima Centauri b has managed to keep its atmosphere, that atmosphere might be thick enough to redistribute heat around the planet. Greenhouse gases could trap warmth and carry it from the day side to the night side. The extreme temperature differences between hot and cold regions might drive powerful atmospheric currents that create a more moderate climate across much of the planet's surface. Recent observations using advanced telescopes have begun to probe the mysteries of Proxima Centauri b. Scientists are looking for signs of an atmosphere by watching how starlight changes when the planet passes in front of its star. They are searching for chemical signatures that might reveal whether this world has water vapor, oxygen, or other gases in its air. The James Webb Space Telescope and other advanced instruments are beginning to study this nearby world in unprecedented detail. These observations might reveal whether Proxima Centauri b has the thick atmosphere needed to support liquid water. They might detect the chemical fingerprints of water vapor or other molecules that could indicate habitability. Future space missions might even visit Proxima Centauri b directly. Scientists have proposed sending tiny robotic probes accelerated to 20% the speed of light using powerful lasers. These spacecraft, no larger than microchips, could reach the Proxima Centauri system in just 20 years and beam back images and data about humanity's nearest exoplanet neighbor. The possibility that a potentially habitable world exists so close to Earth has profound implications for the search for life beyond our solar system. If planets like Proxima Centauri b are common around red dwarf stars, and if red dwarf stars make up about 75% of all stars in the galaxy, then habitable worlds might be far more numerous than anyone previously imagined. Proxima Centauri b also represents humanity's most realistic target for interstellar exploration. While the journey would still take thousands of years with current technology, the development of new propulsion systems might one day make it possible to send robotic explorers to this nearby world within a human lifetime. Tonight, as you close your eyes, remember that just over 4 light-years away, a world not much larger than Earth orbits in the habitable zone of our nearest stellar neighbor. This planet might have oceans in its twilight zones. It might have weather patterns driven by the eternal dance between its day and night sides. It might even harbor life forms adapted to the gentle red light of their small star. The light that left Proxima Centauri b when you were born is just now reaching Earth, carrying with it the possibility that we are not alone in finding ways to nurture the delicate chemistry of life in the cosmos. And as that ancient light from our nearest neighbor arrives at Earth tonight, scientists around the world are preparing to decode its secrets, searching for the atmospheric signatures that might reveal whether distant shores wait beneath alien skies just a cosmic stone's throw from home. Imagine you are holding a crystal prism up to a beam of sunlight. The white light enters the glass and emerges as a rainbow of colors: red, orange, yellow, green, blue, indigo, violet. This simple demonstration reveals one of the most powerful tools in astronomy, the ability to break light into its component parts and read the stories hidden within each wavelength. Scientists call this technique spectroscopy, and it has become the cornerstone of studying planets around distant stars. Every element in the universe absorbs and emits light at specific colors, creating a unique fingerprint that can be detected across the vastness of space. Hydrogen has its signature. Oxygen has its own pattern. Water vapor leaves its distinctive mark. By studying these patterns, astronomers can analyze the atmospheres of worlds they will never visit. When light from a distant star passes through the atmosphere of an orbiting planet, something remarkable happens. The gases in that planet's atmosphere absorb certain colors of light while allowing others to pass through unchanged. This filtered starlight carries the chemical fingerprints of the alien air it has traveled through, like a message written in colors that spans the galaxy. You can understand this process by thinking about how Earth's atmosphere affects sunlight. When the sun is low on the horizon during sunrise or sunset, its light must pass through more of our atmosphere to reach your eyes. The blue light gets scattered away, leaving behind the warm reds and oranges that paint the sky. Similarly, when starlight passes through an exoplanet's atmosphere, certain colors are absorbed or scattered, creating a chemical signature that telescopes can detect. The technique works best when a planet transits in front of its star, as viewed from Earth. During these rare alignments, the planet acts like a thin atmospheric shell surrounding a small dark disk. Starlight passing through this shell gets filtered by whatever gases exist in the planet's atmosphere before continuing its journey to Earth. Sensitive instruments can measure these tiny changes in the star's spectrum, revealing the composition of air on worlds light-years away. Water vapor is one of the most important gases that astronomers search for in exoplanet atmospheres. Water absorbs light at specific infrared wavelengths, creating dark lines in the spectrum like missing notes in a cosmic symphony. When these lines appear in the filtered starlight from a transiting planet, scientists know that water vapor exists in that world's atmosphere. The detection of water vapor tells a profound story. It suggests that liquid water might exist on the planet's surface or in its clouds. It indicates that the planet might have active weather patterns, with water evaporating from oceans and condensing into rain. Most importantly, it means the planet possesses one of the key ingredients needed for life as we know it. Oxygen creates an even more exciting signature. This reactive gas does not last long in an atmosphere unless something is constantly producing it. On Earth, plants and microscopic organisms release oxygen through photosynthesis. If astronomers detect significant amounts of oxygen in an exoplanet's atmosphere, especially combined with water vapor, it could indicate the presence of living organisms. But atmospheric chemistry can be complex and sometimes misleading. Oxygen can be produced by non-biological processes, such as the breakdown of water molecules by stellar radiation. Carbon dioxide, methane, and other gases can create false signals or mask the presence of more interesting compounds. Atmospheric detectives must carefully analyze multiple chemical signatures to build an accurate picture of a distant world's air. Methane presents another intriguing possibility. This gas can be produced by both geological processes and living organisms. On Earth, much of our atmospheric methane comes from biological sources: bacteria in swamps, microbes in the digestive systems of animals, and human agricultural activities. If methane is detected along with oxygen and water vapor in an exoplanet's atmosphere, the combination could suggest the presence of life. The James Webb Space Telescope has revolutionized the field of exoplanet atmospheric analysis. Its large mirror and sensitive infrared instruments can detect incredibly faint chemical signatures in the atmospheres of distant worlds. Webb can study planets orbiting both nearby red dwarf stars and more distant Sun-like stars, greatly expanding the number of worlds available for atmospheric investigation. One of Webb's first atmospheric studies examined WASP-96b, a hot gas giant planet located over 1,000 light-years from Earth. By analyzing starlight that passed through the planet's atmosphere during transit, Webb detected water vapor, clouds, and atmospheric haze. These observations demonstrated the telescope's ability to read the chemical composition of alien skies with unprecedented precision. The technique becomes more challenging when studying smaller, Earth-like planets. These worlds have thinner atmospheres that absorb less starlight, making their chemical signatures much fainter. Additionally, Earth-like planets orbit farther from their stars, so they transit less frequently and for shorter periods. Each observation requires patience and multiple measurements to build up enough data for analysis. Temperature also affects atmospheric chemistry in complex ways. Hot planets close to their stars can have water vapor high in their atmospheres, where stellar radiation breaks it down into hydrogen and oxygen. Cooler planets might have most of their water condensed into clouds or oceans, making it harder to detect from space. The temperature profile of an atmosphere influences which gases exist and where they can be found. Scientists are developing increasingly sophisticated models to interpret atmospheric data from exoplanets. These models consider factors such as stellar radiation, atmospheric pressure, temperature gradients, and chemical reactions. By comparing observed spectra with theoretical predictions, researchers can determine not just what gases are present, but also their concentrations, distributions, and possible sources. Some of the most promising targets for atmospheric study are the planets in the TRAPPIST-1 system. These 7 worlds transit their star frequently, providing regular opportunities for observation. Their cool red dwarf host star produces less interfering radiation than hotter stars, making it easier to detect subtle atmospheric features. Early observations have already provided hints about which TRAPPIST-1 planets might have substantial atmospheres. The search for biosignatures, chemical signs of life, represents the ultimate goal of exoplanet atmospheric studies. Scientists are looking for combinations of gases that would be difficult to explain without biological processes. Oxygen and methane together create a particularly compelling case, since these gases react with each other and would disappear quickly without constant replenishment. But the detection of potential biosignatures will require careful verification. False positives are possible, and extraordinary claims require extraordinary evidence. Multiple independent observations, detailed atmospheric modeling, and consideration of alternative explanations will all be necessary before scientists can confidently announce the detection of life beyond Earth. Future space telescopes will push atmospheric analysis even further. Proposed missions could directly image exoplanets and analyze their reflected light, providing new ways to study atmospheric composition. Ground-based telescopes are also becoming more sophisticated, using adaptive optics and advanced spectrographs to probe the atmospheres of nearby worlds. The field of exoplanet atmospheric characterization represents a new kind of exploration. Instead of sending robotic probes across space, scientists are learning to read the messages carried by light itself. Each photon that reaches Earth from a distant world contains information about the gases it has encountered, the temperatures it has experienced, and the chemical processes occurring in alien skies. Tonight, as you breathe the familiar mixture of nitrogen and oxygen that surrounds Earth, remember that light from distant worlds is arriving at telescopes around the globe. In that light, encoded in colors your eyes cannot distinguish, lie the chemical signatures of atmospheres you will never directly experience. Each spectrum tells a story of pressure and temperature, of chemistry and possibly biology, written in the universal language of light. And in laboratories and observatories around the world, atmospheric detectives continue their patient work of decoding these messages, searching for the telltale signs that might reveal whether we share this universe with other forms of life breathing beneath alien stars. Deep beneath the ice of Europa, or in the warm shallows of a distant exoplanet sea, the same fundamental elements that make up your body are performing an ancient dance. Carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, these 6 elements form the basic vocabulary of life throughout the universe. In alien waters, under foreign stars, these atoms are combining and recombining in patterns that might someday lead to the miracle of biology. You can imagine this chemistry as a slow waltz that has been playing for billions of years. Each element brings its own special talents to the dance. Carbon, the master connector, forms the backbone of complex molecules. It links easily with other atoms, creating chains and rings that can grow into elaborate structures. In Earth's oceans, carbon forms everything from simple sugars to the complex proteins that make your muscles move. In the hidden seas of distant worlds, carbon might be performing the same role. It could be linking with hydrogen to form methane in the cold depths. It could be joining with oxygen to create carbon dioxide that dissolves in the water. Most importantly, it could be building the long chains of organic molecules that serve as the foundation for more complex chemistry. Hydrogen, the universe's simplest and most abundant element, acts like the gentle partner in this molecular dance. It readily joins with almost any other element, providing the connections that hold larger molecules together. In alien seas, hydrogen might combine with oxygen to form water molecules that serve as the medium for all other chemical reactions. It might link with carbon to create organic compounds. It might even participate in reactions that store and release energy. Oxygen brings its own special gift to the chemistry of life, the ability to accept electrons from other atoms. This makes oxygen crucial for the energy reactions that power living cells. On Earth, organisms use oxygen to break down sugars and release the energy stored in their chemical bonds. In alien oceans, oxygen might serve a similar role, helping to power the metabolic processes of extraterrestrial life. But oxygen can also exist in other forms. In the deep, dark waters beneath Europa's ice, there might be very little free oxygen. Instead, this element might be locked up in water molecules, sulfate compounds, or other chemicals. Life in such environments would need to find different ways to harness energy, perhaps by using sulfur compounds or other chemicals as electron acceptors. Nitrogen plays a crucial role as the builder of proteins. This element forms strong bonds with carbon, creating the molecular frameworks that become enzymes, structural proteins, and other essential biological molecules. In Earth cells, nitrogen is part of every amino acid, the building blocks that link together to form proteins. In alien seas, nitrogen might be performing the same function, creating the complex molecular machines that make life possible. Phosphorus serves as the energy currency of life. This element forms high-energy chemical bonds that can store and release energy on demand. In Earth cells, molecules like ATP, adenosine triphosphate, use phosphorus to capture energy from food and deliver it where it is needed. In the alien oceans of distant worlds, phosphorus might be performing similar functions, creating the energy storage systems that power extraterrestrial biochemistry. Sulfur often plays the role of the chemical modifier. It can form bridges between molecules, create reactive sites on proteins, and participate in energy-generating reactions. In Earth's deep-sea hydrothermal vents, many organisms derive energy from sulfur compounds instead of sunlight. In the similar environments that might exist on Europa or Enceladus, sulfur could be providing the energy source for entire ecosystems. The temperature of an alien ocean affects how these elements behave and combine. In the cold seas beneath Europa's ice, chemical reactions proceed slowly but steadily. The low temperature actually helps preserve complex organic molecules that might break apart in warmer waters. This could allow for the gradual accumulation of increasingly complex chemistry over millions or billions of years. In warmer alien seas, perhaps on planets in the habitable zones of distant stars, chemistry proceeds more rapidly. Higher temperatures speed up reaction rates, allowing for faster evolution of complex molecules. But higher temperatures also make fragile organic compounds less stable. Life in such environments would need to develop protective mechanisms or find ways to quickly repair damaged molecules. The pressure in deep alien oceans also influences chemistry. High pressure can force atoms closer together, creating opportunities for new types of chemical bonds to form. It can also protect delicate molecules from breaking apart. In the deepest parts of Europa's hidden sea, pressure might reach levels hundreds of times greater than Earth's atmospheric pressure, creating unique chemical environments unlike anything on our planet's surface. The chemistry of alien seas is also influenced by the dissolved minerals they contain. When water interacts with rocky ocean floors, it dissolves ions of various elements. These dissolved minerals can participate in chemical reactions, catalyze the formation of organic molecules, and provide essential nutrients for any life that might exist. In Europa's ocean, contact with the Moon's rocky interior might release iron, magnesium, and other elements into the water. These metals could serve as catalysts for organic chemistry, helping to speed up reactions that build complex molecules. Iron, in particular, plays crucial roles in many biological processes on Earth and might serve similar functions in alien biochemistry. Hydrothermal vents on the ocean floors of distant worlds could create especially rich chemical environments. These underwater hot springs bring heat, minerals, and reactive chemicals up from deep within a planet or moon. On Earth, such vents support entire ecosystems based on chemosynthesis, the process of deriving energy from chemical reactions rather than sunlight. Similar vents might exist on the seafloors of Europa, Enceladus, or distant exoplanets. Around these warm oases, the 6 elements of life could be combining in concentrated chemical soups. Organic molecules could be forming at accelerated rates. Complex chemistry could be evolving in the warm, mineral-rich waters that flow from deep within these worlds. The formation of the first self-replicating molecules represents one of the great mysteries in the transition from chemistry to biology. On Earth, this crucial step might have occurred in tidal pools, around hydrothermal vents, or in other special environments where the right chemical conditions existed. In alien seas, similar transitions could be happening in environments we can barely imagine. Perhaps in the depths of Europa's ocean, carbon-based molecules are slowly learning to make copies of themselves. Maybe around hydrothermal vents on distant exoplanets, the first primitive metabolisms are beginning to emerge. These processes would be incredibly slow by human standards, taking millions or billions of years to produce noticeable results. The beauty of chemistry in alien seas lies in its universality. The same physical and chemical laws that govern reactions on Earth also apply throughout the universe. Carbon will always be an excellent connector of atoms. Water will always be an outstanding solvent for biological reactions. The fundamental principles that make life possible here could be creating similar opportunities on countless worlds throughout the galaxy. Yet each alien ocean would also have its own unique characteristics. Different temperatures, pressures, and chemical compositions would favor different types of organic chemistry. Life that evolved in these varied environments might look and function very differently from Earth life, even though it would be built from the same basic elements. Some alien biochemistries might use silicon instead of carbon as their primary structural element. Others might rely on ammonia as a solvent instead of water. Some might derive energy from radiation rather than chemical reactions. The possibilities are limited only by the laws of physics and chemistry, which still allow for an enormous range of potential life forms. Tonight, as your own biological chemistry continues its work, your cells burning sugar for energy, your proteins folding into their proper shapes, your DNA quietly copying itself in preparation for cellular division, remember that similar processes might be occurring in seas you will never see. The elements that make up your body are common throughout the universe, and the chemistry that powers your life might be awakening in waters beneath ice shells or around hydrothermal vents on worlds yet to be discovered. And in those alien depths, the slow transformation from simple chemistry to complex biology might be writing the first chapters of stories that will unfold over geological timescales, creating new forms of life that could someday leave their own signatures in the atmospheres of distant worlds. Just as you leave footprints in sand when you walk along a beach, life leaves its own distinctive marks wherever it takes hold. These biological fingerprints, called biosignatures, are the signs that scientists search for when they study distant worlds. They are the whispers of biology carried on waves of light across the vast emptiness of space, telling us that somewhere among the stars, other forms of life might be breathing, growing, and changing their worlds. The most compelling biosignature would be the discovery of oxygen and methane together in a planet's atmosphere. This combination tells a powerful story because these two gases naturally react with each other and disappear. For both to exist at the same time, something must be constantly producing them. On Earth, plants and microscopic organisms release oxygen through photosynthesis. Meanwhile, bacteria in swamps, the digestive systems of animals, and other biological processes release methane. If a distant planet's atmosphere contains both gases in significant amounts, it suggests that biological processes are actively maintaining this delicate balance. The oxygen and methane are like two dancers who can only perform together when life is choreographing their movements. Without living organisms to keep producing these gases, they would quickly combine and vanish from the atmosphere. But biosignatures can be subtle and sometimes misleading. Oxygen can be created by non-biological processes when ultraviolet light from a star breaks apart water molecules in a planet's atmosphere. The hydrogen escapes to space, leaving oxygen behind. This process could create false signals that mimic the presence of life. Scientists must carefully analyze multiple pieces of evidence before concluding that they have detected biological activity. The seasonal changes in atmospheric chemistry offer another potential biosignature. On Earth, the amount of carbon dioxide in the atmosphere rises and falls with the seasons as plants grow and die in the northern hemisphere. During spring and summer, plants absorb carbon dioxide for photosynthesis. During autumn and winter, decaying vegetation releases it back into the air. This creates a gentle breathing pattern that can be measured from space. Similar seasonal variations on a distant planet could indicate the presence of widespread plant life. If telescopes detect regular changes in atmospheric carbon dioxide or oxygen levels that match the planet's orbital periods, it might suggest that vegetation is growing and dying in response to seasonal changes in sunlight. This would be the signature of a living world that breathes with the rhythm of its seasons. Water vapor plays a crucial supporting role in most biosignature scenarios. While water alone is not a sign of life, its presence makes other biosignatures more meaningful. A planet with oxygen, methane, and water vapor presents a much stronger case for biology than a dry world with the same gases. Water provides the medium in which most biological chemistry occurs, making it an essential ingredient for life as we know it. Phosphine, a gas made of phosphorus and hydrogen, represents another potential biosignature. On Earth, this gas is produced mainly by bacteria that live in oxygen-free environments. Phosphine breaks down quickly when exposed to sunlight and oxygen, so its presence in a planet's atmosphere would require constant production. The discovery of phosphine in the clouds of Venus created excitement among scientists, though the detection remains controversial and requires further confirmation. The red edge of vegetation offers a particularly intriguing biosignature that could be detected through direct imaging of exoplanets. Plants on Earth reflect more infrared light than red light, creating a sharp increase in reflectance at the boundary between visible and infrared wavelengths. This feature, called the vegetation red edge, shows up in satellite images of Earth and could potentially be detected on other worlds. Alien plants might have evolved different strategies for capturing starlight, especially around red dwarf stars that produce mostly infrared radiation. These plants might appear black or deep purple to maximize their absorption of available light. They might create different spectral signatures than Earth's green vegetation, but they would still leave detectable fingerprints in the reflected light from their planet. The search for biosignatures requires extraordinary care and skepticism. The stakes are so high that scientists must consider every possible alternative explanation before claiming to have found signs of life. A single unusual measurement is never enough. Multiple independent observations, detailed atmospheric modeling, and careful peer review are all essential parts of the discovery process. False positives can occur in many ways. Volcanic activity can produce gases that mimic biological processes. Chemical reactions in the upper atmosphere can create unexpected combinations of gases. Even the instruments themselves can sometimes produce misleading signals. The history of science includes many examples of discoveries that seemed revolutionary at first but turned out to be instrumental artifacts or natural phenomena. The James Webb Space Telescope and other advanced instruments are beginning to search for biosignatures in the atmospheres of nearby exoplanets. These observations require incredible precision and patience. The signals are incredibly faint, often requiring many hours of observation time to detect. Even then, the data must be carefully analyzed to separate genuine atmospheric features from noise and instrumental effects. Some of the best targets for biosignature searches are the planets in the TRAPPIST-1 system. These 7 worlds transit their star regularly, providing frequent opportunities for atmospheric analysis. Their host star is small and dim, making it easier to study the planet's atmospheres without interference from bright stellar light. Early observations have already begun to reveal which of these worlds have substantial atmospheres. The discovery of biosignatures would represent one of the most profound moments in human history. It would mean that Earth is not alone in harboring life. It would suggest that biology might be common throughout the universe. It would raise new questions about the diversity of life and the conditions under which it can thrive. But even negative results would be scientifically valuable. If detailed studies of many potentially habitable worlds fail to find biosignatures, it would suggest that life might be rarer than we hoped. This would make Earth's biosphere even more precious and unique. It would highlight how special the conditions are that allow our planet to teem with life. The search for biosignatures connects us to the deepest questions about our place in the universe. Are we alone? Is life common among the stars? Do other forms of biology exist that we cannot yet imagine? These questions have inspired human curiosity for thousands of years, and we are now developing the technology to begin answering them. Scientists are also preparing for the possibility of detecting biosignatures that don't match Earth's biological patterns. Alien life might produce different combinations of gases. It might create seasonal variations that don't follow Earth-like patterns. It might reflect light in ways that reveal forms of photosynthesis unlike anything in our terrestrial experience. Tonight, as you breathe the oxygen produced by billions of years of photosynthesis, remember that this gas is one of Earth's clearest biosignatures. It announces to the universe that our planet is alive. If other worlds have learned to exhale their own distinctive combinations of gases into space, then somewhere in the galaxy, life might be leaving its fingerprints in starlight for us to discover. And in laboratories around the world, scientists continue their patient work of analyzing that starlight, searching through spectra and atmospheric models for the subtle signs that might reveal we are not alone in learning how to transform chemistry into the miracle of living, breathing worlds. 1 million miles from Earth, in the cold darkness between worlds, a golden mirror the size of a tennis court catches infrared light from the farthest reaches of the universe. The James Webb Space Telescope floats in perfect balance at a point where Earth's gravity and the Sun's gravity cancel each other out. From this quiet vantage point, Webb peers deeper into space and time than any telescope before it, opening new windows into the atmospheres of distant worlds. You can picture this magnificent instrument unfolding like a cosmic origami flower. Its primary mirror consists of 18 hexagonal segments, each covered in a microscopically thin layer of gold. These segments work together as a single, enormous eye that collects infrared radiation invisible to human sight. Behind the mirror, a 5-layer sunshield the size of a tennis court blocks heat from the sun, keeping Webb's instruments cold enough to detect the faint heat signatures of distant planets. Webb sees the universe in infrared light, the same type of radiation that carries heat from your skin to your surroundings. This infrared vision allows Webb to peer through cosmic dust clouds that block visible light, revealing hidden stellar nurseries and planetary systems in the process of formation. More importantly for the search for life, infrared light carries the chemical signatures of gases in the atmospheres of exoplanets. When Webb observes a planet transiting in front of its star, it performs a delicate act of cosmic chemistry. Starlight passes through the thin shell of the planet's atmosphere, and different gases absorb different wavelengths of infrared light. Water vapor absorbs light at specific infrared frequencies. Carbon dioxide has its own distinctive pattern. Methane creates its unique fingerprint. Webb's instruments can detect these absorption patterns with extraordinary precision. The telescope's sensitivity is almost beyond imagination. It could detect the heat signature of a candle on the surface of the moon. It can measure temperature differences as small as a fraction of a degree. This incredible precision allows Webb to study the atmospheric chemistry of planets orbiting other stars, revealing details about their composition, temperature, and potentially their ability to support life. WASP-96b became one of Webb's first exoplanet targets, a hot gas giant located over 1,000 light-years from Earth. When Webb analyzed starlight that passed through this planet's atmosphere during transit, it revealed the presence of water vapor, clouds, and atmospheric haze. The observations demonstrated Webb's ability to read the chemical composition of alien skies with unprecedented clarity and detail. But Webb's true promise lies in its ability to study smaller, more Earth-like planets. These worlds present much greater challenges because their atmospheres are thinner and absorb less starlight. The signals Webb must detect are incredibly faint, like trying to hear a whisper in a crowded room. Yet Webb's large mirror and sensitive instruments make such measurements possible for the first time. The telescope has already begun studying the 7 planets of the TRAPPIST-1 system. These worlds, huddled around their small red dwarf star, represent some of the best opportunities to search for biosignatures in planetary atmospheres. Webb's observations are revealing which of these planets have substantial atmospheres and what gases they contain. Early results suggest that some TRAPPIST-1 planets may indeed have thick atmospheres that could support liquid water. Webb operates from a special orbital position called the second Lagrange point, or L2. At this location, the telescope maintains a fixed position relative to Earth and the Sun, always staying in Earth's shadow while orbiting the Sun once per year. This arrangement provides Webb with a stable, cold environment and continuous views of deep space without interference from Earth's heat or reflected sunlight. The journey to this distant outpost took 6 months of careful navigation and deployment. Webb's components were folded and compressed to fit inside the rocket that carried it to space. Once in orbit, the telescope slowly unfolded like a mechanical butterfly emerging from its chrysalis. Each mirror segment was precisely aligned using tiny motors that can move them by distances smaller than the width of a human hair. The cooling process took additional months as Webb's instruments reached their operating temperature of -370 degrees Fahrenheit. This extreme cold is necessary because heat from the telescope itself would overwhelm the faint infrared signals from distant worlds. The sunshield acts like a cosmic umbrella, keeping Webb's instruments in perpetual shadow and allowing them to detect the subtle heat signatures of exoplanets. Webb represents the culmination of decades of technological development and international cooperation. Scientists and engineers from NASA, the European Space Agency, and the Canadian Space Agency worked together to create this marvel of precision engineering. Every component was tested and retested to ensure it could survive the harsh environment of space and operate flawlessly for years without the possibility of repair. The telescopes for main instruments each serve different purposes in the study of exoplanets. The near-infrared spectrograph can analyze the chemical composition of planetary atmospheres. The mid-infrared instrument can detect the heat signatures of planets themselves. The near-infrared camera can capture direct images of large planets orbiting far from their stars. The fine guidance sensor helps Webb point with incredible accuracy at its distant targets. Future observations with Webb will push the boundaries of exoplanet science even further. The telescope will study the atmospheres of potentially habitable worlds around nearby red dwarf stars. It will search for water vapor, oxygen, methane, and other gases that might indicate the presence of life. It will investigate how planetary atmospheres change over time and how they respond to the radiation from their host stars. Some of Webb's most exciting observations may come from studying planets that pass directly between their stars and Earth. These rare alignment events, called transits, provide the clearest opportunities to analyze planetary atmospheres. Webb will watch for subtle changes in starlight as it filters through the thin shells of air surrounding distant worlds, decoding the chemical messages carried across space. The telescope's infrared vision also allows it to study the formation of new planetary systems around young stars. By observing these stellar nurseries, Webb can help scientists understand how planets form and evolve. These observations provide context for understanding the diversity of worlds that exist throughout the galaxy. Webb's mission is planned to last at least 5 years, but it carries enough fuel to operate for up to 20 years. Each year of operation will bring new discoveries about the atmospheres, compositions, and potentially the habitability of distant worlds. The telescope's golden eye will continue to peer into the infrared universe, revealing secrets about planets that orbit stars whose light began its journey to Earth before humans learned to write. Tonight, as you prepare for sleep, Webb continues its silent vigil in the darkness beyond Earth's shadow. Its golden mirror collects photons that have traveled for years or decades from distant star systems. Its instruments analyze the faint infrared signals that carry news of other worlds. And in the data flowing back to Earth, scientists are discovering new chapters in the story of planets throughout the universe. Each night brings Webb closer to answering one of humanity's most profound questions: are we alone in the universe? The answer may already be encoded in the infrared light now making its way across the solar system toward Webb's waiting sensors, carrying with it the chemical signatures of worlds where life may have learned to transform starlight into the miracle of biology. Close your eyes now, and let your mind drift beyond the edges of everything you know. Tonight, you are part of humanity's greatest dream. A dream that stretches across centuries, reaching toward distant worlds that circle other suns. Somewhere in the darkness above your head, stars are calling. Each pinprick of light carries the possibility of worlds where water flows and life might flourish. You breathe in, and somewhere in that breath are the same elements that built those distant planets. Carbon, oxygen, iron. The building blocks of dreams made real. Scientists today peer through telescopes the size of buildings, searching the night for signs of home beyond home. They listen to radio waves that have traveled for years across the emptiness between stars. Sometimes, in the static and silence, they wonder if someone else is listening too. You are part of this listening. Every time you look up at the night sky, you join a conversation that began when the first human noticed stars moving differently than others. Those wandering lights were planets. Worlds like ours, but impossibly far away. The nearest star with planets sits 25 trillion miles from Earth. If you could drive a car at highway speed toward that star, never stopping, never slowing, your journey would take 28 million years. Your great-great-grandchildren would be dust before you traveled even 1% of the way. But distance has never stopped human dreams. We are the species that looked at oceans and built ships. We saw mountains and learned to climb. We watched birds and eventually soared higher than eagles ever could. Now we look at stars and plan journeys our children's children might take. Space telescopes drift in the darkness above our atmosphere right now, watching for the tiniest dimming of starlight. When a planet passes between its star and Earth, the light dims by just a fraction. But that fraction tells a story. Scientists can read the size of that world in the dimming. They can taste its atmosphere in the colors of filtered starlight. Some of these distant worlds sit in what astronomers call the habitable zone. Not too hot, not too cold. Just right for liquid water to pool on their surfaces. Water that might cradle the first stirrings of life, just as it did billions of years ago in Earth's ancient oceans. Imagine those alien seas tonight. Perhaps they are blue like Earth's, or maybe green with different minerals. Maybe they are orange under the light of a red dwarf star, or silver beneath twin suns. In those waters, molecules might be dancing the same ancient dance that began life here. Carbon linking with carbon. Forming chains and spirals and intricate patterns that learn to copy themselves. You carry that same dance in every cell of your body. The same chemistry that might be awakening on 1,000 distant shores flows through your bloodstream tonight. Life recognizes life, even across the vast emptiness between stars. One day, humans might sleep in ships between the stars. Not the quick sleep you know, but something deeper. A slow suspension of time while decades pass like seasons. They would dream their way across the darkness, carried by technologies we can barely imagine today. Or perhaps they will send their minds ahead, encoded in beams of light that travel at the universe's speed limit. Consciousness itself becoming a message in a bottle, thrown across the cosmic ocean. Those minds might wake up in new bodies, built from materials waiting on distant worlds. But the journey has already begun in smaller ways. Every space probe that visits Mars or dives through the ice of distant moons carries a piece of human curiosity with it. Every photograph sent back from those worlds expands the borders of home just a little further. Robot explorers swim through the hidden oceans of Europa tonight, beneath miles of ice. They taste the salt water that has stayed liquid for billions of years, warmed by the pull and stretch of Jupiter's immense gravity. They search for the chemical signatures of life in places where sunlight has never touched. On Mars, rovers no bigger than golf carts climb ancient riverbeds, reading the story written in stone and dust. They find evidence of water that flowed when Earth's first complex life was just learning to breathe oxygen. Perhaps life once flowed there too, in streams that caught the light of a younger sun. You are connected to these metal ambassadors by invisible threads of radio waves and human wonder. Each discovery they make becomes part of your story. Each photograph they send home adds another room to the house of human knowledge. Tonight, as you settle into sleep, you join the long dream of your species. The dream of touching alien shores and greeting whatever life might wait there. The dream of answering the question that has haunted every human who ever looked up at the stars: are we alone? Your breath slows now, matching the rhythm of a species learning to walk between worlds. In your dreams, you might glimpse those distant oceans. Feel alien winds carrying the scent of life that evolved under different constellations. And when morning comes, the stars will still be calling, patient as the tide, waiting for humanity to learn how to answer.